Good morning, good afternoon, good evening. My name is Salman Basit, and I'm a product manager at MongoDB with a security and compliance focus. I'm excited to describe how you can use MongoDB to implement cryptographically verifiable change history. Because this presentation contains forward-looking statements, I have to present the safe harbor statement. Here is the agenda for the talk. First, I will motivate why cryptographically verifiable change history is needed. I will then describe the goals of the talk and what is meant by change history. I will then give an overview of proof of concept with links to the GitHub code. Finally, I will explain what is meant by cryptographically verifiable change history and how it has been implemented in the proof of concept. Let me motivate the need for cryptographically verifiable change history using 4 examples. That is drug development, banking transactions, digital assets, and financial reporting for public companies. Drug development is a very long and complex process. It is divided into 2 distinct parts, preclinical and clinical. Each part involves multiple stages or phases. The end goal is simple: ensure that the drug released is safe for usage. Drug development is governed by good practices or GXP regulations. While the GXP guidelines are generally similar across countries, typically each country has its own regulator for drug release. In the US, Food and Drug Administration regulates the drug development. The goal of these regulations include traceability and data integrity. Traceability means the ability to reconstruct the development history of a drug. Data integrity implies making sure that the data for drug development and its history are free from manipulation and breaches, because data manipulation for drugs can have serious consequences. So if you are a developer designing an application to manage data for development of any drug, you may wonder that could you record drug development history in an easy way for reconstruction? And could you as a developer implement measures such as digital signatures and cryptographic verification to detect data manipulation? Let's take another example of a banking transaction. You visit an ATM or a cash machine. You check balance. The balance is $100. You withdraw $20. The remaining balance is $8. Finally, you print a paper receipt from the ATM, which is issued to you by the ATM. So what is the online equivalent for this transaction? You visit the bank website by logging in with your username and password. You check the balance. The balance is $100. You transfer $20 to another account. The remaining balance is $20. Perhaps you get an email of a transaction from the bank. Or perhaps you can print a screenshot of the remaining balance. The question is, do you consider these 2 transactions and their confirmations to be equivalent? That is, what is the online equivalent of ATM printing the remaining balance on a piece of paper? Perhaps your bank can issue you a digital receipt of your transaction and balance when you log out of the website. Let's take another example. In the digital assets or crypto world, crypto assets are owned by a customer if they are in sole possession of a cryptographic private key associated with the digital asset. The cryptographic public key associated with the crypto asset is typically stored in a public decentralized ledger, such as a Bitcoin network. It really requires a technically savvy user to store and manage private keys associated with digital assets without a third party. Thus, non-tech savvy users delegate the management of keys to a third party. Often that third party is the crypto exchange. The crypto exchanges hold these private keys or digital assets on behalf of the customer without sharing the private key with the customer. Customers log in into the crypto exchange as they trust it. Thus, an interesting problem arises. How does the crypto exchange prove to a customer or potentially to an auditor, that it holds digital assets or private keys, so-called proof of reserve, without revealing those private keys to the customer or the auditor. So as a developer, you may be thinking, if you could design a cryptographically verifiable mechanism to prove to an auditor or a customer that your crypto exchange was in possession of digital assets at a certain point in time, such as every day. Let's consider the final motivating example. Sarbanes-Oxley is a law that was enacted in July 2002 in the US to oversee the audit of public companies that are subject to the securities laws. The major elements of the law include auditor independence, corporate responsibility, and corporate fraud accountability. While the law provides strict penalties against such fraud, the reality is that the data that is needed for corporate disclosures for securities is stored in databases and has the potential for manipulation. The question for you as a developer is that can you create mechanisms to make it easy to detect tampering of data associated with corporate disclosures? Hopefully through these examples, I have motivated enough the need for having a cryptographically verifiable change history. Now let's talk about the goals of this talk. The goals of this talk are twofold. First, I will describe how one can use MongoDB to implement cryptographically verifiable change history while preserving MongoDB query language and API interface. I will explain the proof of concept implementation. The second and more important goal is, if this idea resonates with you and you would like to see the proof of concept more natively implemented within MongoDB drivers or server, we want to hear from you. Please send an email to customer-security-working-group@mongodb.com with the subject "Join to get involved." So let's talk about what is change history. Informally, it is the history of change for an entity going back to some reference origin. Going back to the banking example, suppose you open a bank account. It has $0 in it when the account is opened. Then you deposit $100 on day one. Then you withdraw $20 on day two. As a bank account owner, you want to go back and see transactions from last day. Or you may want to see transactions since you opened the account. But the bank has to track your account history all the way to when you opened your account. So why is change history needed? Broadly speaking, there are two main reasons. First, an application may require change history to be maintained. For example, a bank has to maintain the history of transfers and withdrawals to the accounts. Similarly, drug development history has to be maintained. Secondly, there may be information security and compliance requirements that not only require maintaining of change history, but also ensuring that it is not tampered with. These requirements are not mutually exclusive. The focus of this talk is going to be on application requirements for maintaining change history and ensuring that the data is not tampered with. What does change history mean in a database or MongoDB context? For this talk, I define the change to be creation, updation, or deletion of data in MongoDB. So you may be wondering, what about read? For some application, the fact that a sensitive data has been read can also be considered a change. But for the purpose of this talk, we only consider the change to be creation, updation, or deletion of data. What could change history conceptually look like with MongoDB? Say you insert a document in MongoDB by calling insert. This operation creates a document and assigns a randomly chosen ID to the document if not specified within the document. Next, you may want to update the document. So you specify the document ID and specify the fields to be changed. When the update operation completes, what should be the end result if some type of change history flag was on? Conceptually, a full new document can be created which has the most recent changes while the original document resulting from the insert operation remains intact. Then when delete is called, the document should no longer be accessible through regular MQL operations on a collection. But it does not mean that the document and its change history should be deleted altogether. Instead, conceptually speaking, it should be recorded that the document was deleted. Perhaps another operation needs to be introduced which would purge the change history of an entire document, for example, for GDPR purposes. At this point, you may be thinking, isn't this what MongoDB audit log does? For example, when insert is called, and auditing is enabled with audit authorization success, then an event like the one shown next to the document being inserted is emitted and stored in the audit log. Similarly, when an update operation is performed, an event like the one shown next to the document being updated is emitted and stored in the audit log. So what is the challenge? The challenge is that audit logs are stored in files outside the database storage engine. It has to be this way. Otherwise, someone can change audit logs stored inside the database storage engine. More importantly, it requires the developer to implement code to retrieve change history from audit files. This can be done, but can require significant work. Obviously, as MongoDB, our goal is to make it easy for you as a developer to write applications. If you have to do a ton of work to implement change history, that is not desirable. Let's make it more concrete by considering the example of a financial website that is required to show its users all the changes they have made to their accounts, such as address changes. The most recent update of the user should be visible upon login. How can this application implement the change history? There are a couple of options. In the first option, the application can maintain two collections. The first collection contains the most recent updates for a document. The second collection, titled History Collection, contains all the previous versions of the document, including the latest version of the document. This approach allows an application to continue to operate with MQL on the main collection for the common case of showing most recent updates upon login, while retrieving all previous updates from the history collection. We have implemented this approach in our proof of concept. The other options include storing a full copy of the document within the same document or within the same collection. These approaches run into challenges such as document size and also require application changes to retrieve the most recent version of the document, since all the previous documents are stored within the same collection. Let me now describe our proof of concept. The proof of concept implements cryptographically verifiable change history. I will describe the crypto part after explaining how change history is implemented. Expanding on the stated goal of using MongoDB to implement cryptographically verifiable change history, we have put together a proof of concept to make it easy to implement change history while preserving MQL. We use a separate collection to store all updates to documents within a collection. In the proof of concept, we have implemented it at the client side, so that all crypto operations relating to insert and update happen on the client side. Specifically, the proof of concept defines the following methods in a Python library. That is, insert one ledger, update one ledger, verify one ledger, and delete one ledger. If you notice, these methods follow the convention of PyMongo insert one, update one, and delete one methods. Using dynamic type creation in Python, these methods are added to the PyMongo object at the startup. Thus, as a developer, you can use the PyMongo object in your program and call these methods just as you would call existing PyMongo methods. These methods automatically manage the storage of data in a separate collection. That collection is suffixed with _history. The GitHub code for this proof of concept is available on MongoDB Labs. Let's go in more detail. In this example, a developer calls the insert one ledger method implemented in the proof of concept library to insert the data into customer's collection. The method automatically handles the insertion of data in customer's history collection. The method uses MongoDB transactions to ensure that both writes happen within a single transaction. The developer then calls the update1ledger method with the document ID and aims to update some fields of the document. The method updates the data in the customer's collection and also adds the latest version of the document to the customer's history collection. Then a developer calls the Verifiable method, which checks whether the most recent version of a document or its history has been tampered with. Finally, a developer calls the delete1ledger method, which deletes the document from customer's collection. However, the document is retained in the customer's history collection. The previous description only showed how change history is implemented in the proof of concept. Let me now elaborate on how proof of concept implements the cryptographically verifiable change history. Informally, if a document has been inserted, updated, or deleted, a user wants to verify that the document or its history has not been manipulated, such as upon retrieval. To recall, the benefits are enhanced data integrity for applications. Let us consider a previous example of the financial website. A financial website user adds or updates their information in the website. The website then returns crypto evidence of their information, perhaps in the form of a QR code, to the end user, which the user stores in their mobile wallet. On subsequent logins, the user can use the QR code to validate that the information it provided previously matches the one returned by the website. In the previous example, a user is either a developer or an application user. The developer obviously uses MongoDB for storing and retrieving documents. The application user uses the website to store and retrieve information. The website uses MongoDB. So who can manipulate the change history? It can be any number of factors. It can be the DBA, or a developer, or an application user, or a malicious actor. So what does manipulation look like? In this example, the most recent version of a document and its history has been manipulated, as shown by the red color. How does proof of concept implement cryptographically verifiable change history using hashing? First, a developer calls the insert1ledger method to insert a document, just as it would for a normal insert1 method. The method then computes a SHA-256 hash of the document. Given that two documents can be identical without underscore IDs or document IDs, if an underscore ID is not specified, the method automatically generates it and uses it in the hash computation. The method then invokes the regular insert1 method to insert the document into the target and history collection. This operation is performed using MongoDB transactions. At some point, the document may need to be updated. The developer calls the API to update the document using regular set operations, shown in bold for city and state. Since the hash must be computed over the entire document, first, the $set updates must be applied to the document to determine the latest version. And then this is a critical step. A cryptographic hash is computed over the most recent version of the document and the hash of the previous version of the document. This operation forms a hash chain between the document history and allows us to traverse the change history to verify it cryptographically. Lastly, the update1ledger method in the proof of concept calls the regular update1 method to update the document in the target collection and also insert the document in the history collection. These methods are wrapped within MongoDB transactions. You may be wondering that developer still has to do the work because insert, update, delete methods are different from the regular insert1, update1, and delete1 methods. You're right, but this is a proof of concept, and that is why we need your feedback in considering the right interface. Another possible option we have considered is if at the time of collection creation, a flag can be specified that the collection is meant as an append-only ledger. Then the developer would call the regular insert and update methods, and the change history and crypto magic happens automatically inside these regular methods. The proof of concept introduces a new method, namely verify one ledger, to explicitly verify a document and its chain history. But that is not the only possible option. Potentially, cryptographic verification can be performed on every read or write. Perhaps it is best to expose these options as knobs to you, the developer, in a simple way. That's why we need your feedback. Depending on the application, the crypto verification can be performed over a single document and its history, or over all documents in a collection and their history. Again, this is a place where we look for your feedback in determining what may be the right choice, or whether these options should be exposed as choices to you. Conclusion. In this talk, I have described how one can use MongoDB to implement cryptographically verifiable change history while preserving MQL and API interface. I have also described a proof of concept implementation. The source code of this proof of concept implementation is available at github.com/mongodb-labs/ledger. If your application has a need to implement a change history with or without crypto verification, we would love to hear from you. Help us build a roadmap by sending an email to customer-security-working-group@mongodb.com with the subject join to get involved. Thank you for listening.